All right, everyone. Welcome to ITC Colloquium. It's my great pleasure to introduce today's speaker, Professor Paul Shellard. Paul is now the director of Stephen Hawking Center for Theoretical Cosmology. Paul has been doing significant contributions to the field of theoretical cosmology throughout his career, starting with many of his foundational work on cosmic strings and topological defects. Earlier in his career, Paul, together with Alex Valenkin, co-authored a textbook which has remained in this subject, which has remained as a classic and a standard textbook over 3 decades. In recent decades, Paul has extended his research interest to the physics of primordial universe, including inflation model, density perturbations, non-Gaussianities, and their manifestations in CMB and large-scale structure. Paul and his collaborators' work on non-Gaussianity analysis has been one of the backbones of the CMB data analysis, notably in the publication of Planck team's paper on non-Gaussianity and the inflation model. Those works has been essential in revealing the implications of the CMB data for the physics of primordial universe. So let's welcome Paul.
Oh, thanks. All right. Okay. Thanks very much. I'm very grateful for the kind invitation to come back to Cambridge, and also to realize that the weather's not just bad at the old Cambridge. Anyway, so I'm just going to tell you about my enthusiasm for probing the early universe using the latest observational surveys, and especially using the bispectrum as a diagnostic tool. And so this is a personal view. It's not an overview of the whole field, but rather it's just telling you about the sort of program we're embarked on in Cambridge with my long-term collaborator, James Ferguson, and our students. So these are my students, David Baker, Alex Maranthus, Bowie Zhang, and then former student of James, Wu Yun Sun, and Peter Suman, now a student, and Donggang Wang is a postdoc in Cambridge at the moment. So I'll tell you some of the results and the updates beyond what we've done with Planck. So, as you know, we've got a lot of cosmological information out of Planck, and most of it comes from the power spectrum, all these cosmological estimates. We've got good concordance with the idea of nearly scale-invariant Gaussian initial conditions from inflation. Don't think that's under threat really from things like late-time H0 dissonance that there appears to be. That could be some sort of late-time evolutionary effect in the universe if it's not a systematic effect. So we've got great progress on that, and then we've got very significant constraints from Planck and from BICEP in particular, pushing down the number of the tensor mode limits, and then we've got very good measurement of the spectral index, and so that's put a lot of inflationary models under pressure. But we can get more insight from the bispectrum, because Gaussianity will break down at some level, and we'll get some unique insights eventually if we keep the sensitivity going. So higher order correlators can reveal new interactions in the early universe, which was the idea of the picture at the beginning on my first slide, which is the idea that we see a cosmological collider in the early universe. We see the interactions between particles. And then we also have nonlinearity developing from gravitational effects subsequently. Okay, so the bispectrum is the 3-point correlator, or the Fourier transform of it, and it's considerably more difficult to estimate. You have to get these triangles in all these possible orientations. So it's many more operations in principle than the power spectrum, but I'll show you why that's not actually the case. So what's interesting is the fascinating thing about inflation is that we're probing such early times, and we're getting this remarkable insight back at maybe 10 to the minus 35 seconds after the Big Bang. And although inflation is probably only a lower energy effective theory for something more fundamental, it's probably the most likely place where we get the clearest view of what that fundamental theory is. We'll get some signatures or some hints about what underlies inflation and learn more. Okay, so the bispectrum is important in that because it can reveal these nonlinear interactions. Okay, so what's interesting is, of course, that we have that inflaton field way back, and we see its effects through, the potential it creates in the cosmic microwave background. But the problem with that also is that this nonlinear clustering continues into the late universe, and it obscures some of the information that we had in the primordial universe. And so the CMB is pretty okay, but obviously it passes through nonlinear clustered objects, and we get lensing and other effects on it. But it's particularly important when analyzing large-scale structure surveys that we understand the two signatures from late times and early times, and we're able to distinguish them. Okay, so let's remind ourselves a little bit about bispectrum. So the bispectrum is the next order from the power spectrum, which we're all familiar with. It's the three-point correlator, and these momentum vectors must close and form a triangle for momentum conservation. And this triangle condition means that the bispectrum actually lives in a tetrapid, okay? So triangles outside, so here we have, if we have isotropy, we only need to know the lengths of these vectors, okay? So the K1, K2, and K3. And so if we live outside this tetrapid, then the triangle doesn't close, okay? And so this is a bit of an inconvenient domain for a lot of calculations, but that's what we have to live with. And then what we're interested in is essentially we can define the sum of these k's going along the equilateral direction, okay? And that's telling us the scaling of the bispectrum. And then we're interested at a particular, so that when we talk about scale invariance, we mean we're just the same in all these directions, in this direction. When we're talking about the profile, we're looking across this scale invariance signal. And when we talk about the envelope, then we're talking about breaking scale invariance and having a particular signal like this. So here's a scale invariant signal from local non-Gaussianity. So here we're looking at this face here that we've cut in this orthogonal to the equilateral line. And so here we have all the signal in the corners, okay, in this squeeze limit where one of the k's is very small. Okay, that's just one example. Okay, so now we have to project this primordial bispectrum in K space into L space, multipole space. This is a little bit more complicated than large-scale structure, but essentially the same things are happening. So where previously we had a very uninteresting power spectrum and it turned into all these lumps and bumps because of acoustic oscillations, now we get all these acoustic oscillations appearing in the bispectrum in a very similar way. Okay, and the bispectrum likewise lives in a tetrahedron, and on top of this tetrahedron is this L max, which tells you where the observational data cuts off, so we get a little more information up here in the green section. Okay, so this is the angular bispectrum, which we project. So we've got our primordial bispectrum, where we're making some prediction from inflation, and then we're projecting it through transfer functions, through all these just something obtained from CAM or class. And then we're projecting it from K space into spherical transforms, into L multipole space. Okay, and then when we worry about whether things are consistent with each other, what degree of correlation we have, then we consider inner products of the projected bispectrum with other projected bispectra or with the data. Okay, so we endeavor to find the bispectrum in here, and we project the bispectrum, the primordial one, and take the inner product to see what our signal is. So here's this squeeze signal. This is the local signal I mentioned before with all the signatures on the edge. And this is typical of a multi-field model where you have light fields providing extra additional signatures. If you have a single field model where you had heavy fields which you've integrated out, or you have extra dimensions like a dBi inflation model, then you get the signature in the center. And then if you have an excited model, then you often get the signature on the outskirts of the tetrahedron. This is also the signature of gravitational collapse, or the initial stages of it. So then you project these and get the CMB bispectrum, which looks like the following. And these are old constraints. I'll give you the latest Planck ones later. Okay, and so it's the distinguishing these different types of non-Gaussianity, which is what our goal is with observational surveys, and Planck has been very successful in constraining these models. Okay, so we've got the three basic types. We've got these equilateral ones, okay, and you'll see Xingang's name here many times. He's one of the leaders in non-Gaussianity and theoretical advances in this area. And it was great to have him in Cambridge as a Stephen Hawking Fellow when we were first looking at the Planck results and to get his advice. And so you're very privileged to have him here, actually in the new age when we're switching over from the CMB to large-scale structure. Okay, so then you have this equilateral shapes, you've got the squeeze shapes, you've got the cosmological collider, which I'll tell you a little bit more about, which is where you exchanging massive particles with a mass scale comparable to the Hubble radius, the Hubble scale during inflation. And then I'll also focus a little bit on oscillatory feature models, just because I can't go through everything in this short time. Okay, so that's the theory side of things and how you project them to make a prediction today. And now what about the estimation? Okay, well, the estimator is bringing the two together. So we've got our theoretical estimator here, okay? And so this is very difficult thing because this is five-dimensional integral. It's basically intractable if you were to do it. So what you really need, and the only sort of shapes that people have looked at are really these separable ones. You need to break this bispectrum down into parts so you can take this three-dimensional integral and make it into one-dimensional integrals, okay? And so that's what people have done with the KSW approach, pioneered during the WMAP analysis. But we took this further and said, well, let's use separable eigenfunctions to expand any shape, okay, whether or not they're separable inherently. And so that's the idea here. We take a set of eigenfunctions which are products of some basis, sine, cosine, Legendre polynomials, very convenient. But remember, they're on a tetraped, okay? They're a tetrahedron, so they're not orthogonal in the usual way, so we have to orthogonalize them, and that brings certain complexities, which I'll talk about later. So on the one side, we have this expansion of the theoretical bispectrum, for which we use alpha, and then we have the estimated bispectrum, which is we use beta. Okay, and so the difficulty with this estimation approach is the fact that these eigenfunctions, like Legendre polynomials, are actually overcomplete. So we actually have to select from them because we can't invert this matrix of inner products reliably. The condition number is too small. Okay, so let's talk about the actual data now. Okay, so we've got our we've got our primordial basis, and we're projecting forward what we think this primordial spectrum should look like in the CMB. And then we've got our CMB basis. Okay, so we expand our late time results in terms of a similar, in multiple space, a similar set of eigenfunctions. We choose to use Fourier modes generally in the late times and Legendre polynomials early. Okay, so this is our projection. So we have to project here, and then we have to convert our projection into the basis we're using for the CMB analysis. Okay, so that's the basic idea. And then we actually expand our CMB version of the bispectrum in a signal-to-noise weighted version, okay? Again, with separable eigenfunctions. Okay, so here's the basic idea. The estimator is finding this inner product between the predicted bispectrum and the estimated bispectrum. So there's the ALMs, the three-point correlator brought together. If we have a separable basis, then these all break up into single sums like this, so it becomes very simple again. We are basically filtering the data with an eigenfunction, and then we're finding the three-point correlations between the eigenfunctions with each other. So we've got the three sets of filtered maps multiplied together and summed up. And so then we have our predicted coefficients here, and then our observed coefficients from the data, and we bring the two together, and that's our FNL. Okay, that's how much of that non-Gaussian signature is there. Of course, this is, there are many confusions for this, many systematic effects like the mask, which produces naturally a very local type of non-Gaussianity, which we have to subtract out. Then we've got noise, beams, and so forth, inhomogeneity. And so we subtract out these through simulations and the covariance of the simulations, and take out this linear term here, which reduces our variance a great deal for certain types of non-Gaussianity, and in particular for the local type non-Gaussianity. Okay, so that's the end result. But a side effect of this extraction of the signal from the CMB map, here's our late time map, foreground cleaned from Planck. We're able to actually get the betas. I should have beta here, and we can actually reconstruct the signal-to-noise weighted bispectrum. Okay, and this is what it is. Okay, this is the Planck. This is the bispectrum of our universe according to Planck. Okay, and so here we've chopped our tetrahedron in half just to reveal the center. The equilateral part is along here. So here's the cut we've done. There are lots of copies of the bispectrum because it's a symmetrized quantity. So what you want to look at is the squeeze limit is on the edge over here. Okay, and then we have the flattened limit, that's the face here, and then the equilateral is through the middle here. Okay, and you can look at this. There's actually one real signal here. The rest might be just noise. The real signal you can see along this edge. I'll discuss that in a second. But if you imagine, perhaps there's an oscillatory model here. You see blue, red, blue, sort of a gap, orange, blue, red, blue. Sort of maybe there's something revealing itself there, and this is not in this is not in synchronous with the actual acoustic oscillations.
Sorry, I'm missing something.
Yeah, sure.
So how do we tell if it's noise or signal? Because you didn't. Are you calibrating it by some noise?
Well, yes, this is the big question: is this noise or signal?
So how do you
and
know
and that noise calibration is very difficult because when we get the Planck simulations, they have a certain level of noise.
Right.
Yeah. And when you integrate these things, I mean, it's certainly noise dominated up at the top here, And that's why when we get the cross correlations with the polarization, you know, we cut off much earlier because this is just noise dominated. So that's a very interesting question. And so are we just cross correlating stuff with noise? Well, anyway, perhaps a good illustration of the fact that there is signal here is this ISW lensing signal. Okay, so this is predicted to be at a certain level in the squeeze limit, and you can see the blue sort of oscillatory signal along here, which comes out at about 3 sigma. Okay, so that shows you the sort of level of noise. So I think it's a very interesting question, but we've been really unable to bear down on this issue of whether that's a non-Gaussian signal or whether it's pure noise. Anyway, we look for non-Gaussian signals in there, regardless, and there is one of them. Okay, at the predicted level. Okay, so just to remind you that this is a 3-dimensional object. This is it rotating around, so it's completely noise dominated at the top, but perhaps there's some indications or hints of non-Gaussianity in the center there. Okay, so there's the same thing that can be done with large-scale structure as well.
Presumably there are uncertainties, error bars associated with each of the data, which is not shown in this color scheme.
Oh,
related to
yeah, yes, of course, yes. We have many foreground. We have several foreground clean maps, and we evaluate the bispectrum from all of them. They're all self-consistent with each other. Okay, so from these, we obtain the standard constraints on local, equilateral, and orthogonal shapes with several estimators. So this is very validated across several groups, and our modal method. So these are just targeting these particular shapes, but these are sort of general modal methods that we're using. I said there's a feature model there. The earliest data releases from Planck indicated perhaps 3 up to 4 sigma feature models, but they sort of damped down over time. So we've ended up with just a 3 sigma sort of signal there, and here's that sort of best fit model. There's the theoretical feature model, and this is what it projects to in the late time. And but our enthusiasm for that, was diminished as the polarization data became available and so forth. And so our best fits are not very high; they're just about 3 sigma level. But of course, you know, there's a look elsewhere effect here. We're looking across many models, and so in fact, that's about the level you would expect randomly to get a signal. So we don't have strong evidence for feature models, and we've looked across many other models. I won't trouble you with all those, but all the well-known inflation models, we've searched for them in this data. Yeah.
If that feature were real, what would it represent?
If that were real, yes, I'll get to that in a second.
Okay.
It's when you have an inflationary model, and there's a sort of step in the potential, okay, and that creates an oscillatory signal, okay, and there's a resonance type where you actually have features that you imprint, like in an axion type model. Yeah. So this is the sort of the picture of what's required for this. We put in the Planck clean maps here. We filter them, extract the actual reconstructed bispectrum here. So that's from the observational side, and then we bring down this beta and we confront it with the theoretical predictions. Okay, so this is some sort of template we've got from inflation, and project it forward into this theory bispectrum here. Okay, so what's happened since Planck? Oh, I just want to comment. This is especially if you do this for large scale structure, this is large memory operation here because you're filtering your whole data set and then you're summing it together across all the possible combinations of eigenfunctions. So you want a lot of memory and you need a high network bandwidth to communicate. And then this part here is lots of integrations on the tetrahedron, lots of inner products. It's a small scale, very suitable for offload to GPUs and on big supercomputers. So what's advanced since the Planck data? Well, we've got a bit fed up with using approximate templates from inflationary models. So we've actually implemented numerically the primordial, the in quantum field theory formalism, so we calculate directly what the initial primordial bispectrum is. This uses an orthogonal set of eigenfunctions, which is quite simple. And so we've also adopted an orthogonal set of eigenfunctions for a similar modal estimator here. This is work of Philip Clark, a former student, and being undertaken by Bowie Zhang now. And this is by Wu-Yung Sun. Okay, and so these can connect together much more directly. And we've done this in order to do model selection. Then we've also advanced this sort of same technology to large-scale structure, though it's very much more complicated there, and we will need much more insight from observers as to how to remove systematic effects. But we still have the highly efficient methodology, separable methodology, and we can reconstruct the bispectrum from large-scale structure surveys. Okay, so let me just quickly comment on the primordial precision bispectra that we can extract. So this is the sort of in formalism, Schwinger-Keldysh integrals, where you have an interaction Hamiltonian. So these are the corrections to the sort of Bunch-Davies vacuum you're predicting from inflation, and they're appearing in the bispectrum. So you're directly calculating these accurately. And again, what we found was that this work was originally done by Funakoshi, a student of mine, and Reno Patel, but we've actually turned it into a much more practical pipeline for doing this very rapidly. Sorry, I've rushed forward there. So with separable methods, you can similarly reconstruct a highly accurate bispectrum predicted by a specific inflationary model. This is this is DBI inflation, the exact shape rather than a template, and this is a particular oscillatory model. And using different types of eigenfunctions, you get different levels of convergence, but you can get your bispectrum on the full observational domain at precision of 10 to the minus 6, more than you'd ever need observationally, okay, and is much, much faster than existing methods. But these have been very useful. This is the pi transport method, have been very useful for validating this approach. So we can do template-free analysis which gives us a direct link to fundamental parameters. So here's this example of a feature model that I was mentioning. So you're rolling down your inflationary potential, and then you hit this little feature. It's got, say, 3 parameters. You've got where is that feature appearing, okay, during inflation. So that determines your K, what's its width, and how big is it, how high is it. And this is the sort of typical model you would expect from that. And there's this template which we searched for in the Planck data showing the sign and where we've chosen an arbitrary phase. However, if you make this feature a little bit stronger, have a slightly sharper gradient here, then you start to actually have back reaction on the Bunch-Davies modes. You get an excited state. This is sort of non-Bunch-Davies here. And you get a sum of the original oscillatory signal plus this non-Bunch-Davies part, okay? So both of these are quite well captured by the Planck templates that we looked for. But if you notice carefully, they're slightly out of phase with each other. And so the end result is really quite a different signal, which the Planck templates don't pick up on very well. They'd only get a 60% correlation with this. And so indeed, a 3 sigma signal could turn into 5 sigma or be quite exciting. So that's how we're following up using this much more accurate analysis of actual signals rather than analytic approximations. So there's certainly Planck discovery potential that remains. And in particular, we're interested in this oscillatory type models, and we will update the constraints on that in due course. What's exciting, of course, is that a 3 sigma signal for CMB-S4 would become a 6 sigma signal, okay? So if these hints were actually to emerge as something real, then the next generation of CMB experiments would observe them. Yes? Yes, and I would hand that question over to Xingang. Perhaps at the end. There'll obviously be a breakdown in this linearized perturbation of the in formalism if you overdo it. But I don't think this regime is the problem. The problem is when you come to predicting things like primordial black holes and you're going to extreme variations. Yeah. Okay. Anyway, so these sort of shapes are available. So there's discovery potential. It also means that when you use this actual primordial bispectrum, you get a much closer connection between the parameters in your model. This is just a DBI example, which is inspired by brain inflation. You have these particular modes here, and we're able now to look for the predicted power spectrum and the bispectrum both at the same time, which is quite difficult to find models that actually work. So the green area is where the power spectrum is okay, and the red area is where it's excluded. And so then we're able to see, well, what models are actually consistent with Planck. And you can see that some models are producing too much null Gaussianity. And so that means we have a much improved constraint on this particular beta, which is determining the non-Gaussianity in the model. And we've got a 2 times improved constraint on that relative to Planck. And the same for the sound speed. And so that we're just about to publish this paper. We were meant to finish it before I gave this talk, but we didn't quite get there. But it's just a proof of concept how you can connect Planck to fundamental theory directly. Okay, so a very popular area is the cosmological collider. So let me tell you about some new results on that. This is using the CMB best modal method from Woo-Yun Son. And this uses orthogonal eigenfunctions, which, as I said, can connect very nicely to the primordial basis, okay, for the primordial bispectrum. Okay, this may be less efficient than the old modal method, but it minimizes these transformational losses when you switch from one basis to another. Okay, and what's interesting about this CMB best is that there's also a public version. If you have your own primordial signal or primordial bispectrum that you think is interesting to look for, then you can use this code to decompose it into eigenfunctions to find the coefficients for the expansion. The thing you have to check is that the basis actually converges well for your particular shape. But using that, you can use the pre-computed Planck bispectrum coefficients, put the two together, and you get an immediate constraint or perhaps discovery of the signal that you're looking for. Okay, so that's available online. Now, one of the most interesting things that Planck didn't look for was the cosmological collider. This is proposed by Arkani, Hamid, and Maldacena, and also Xingang before. But they did this interesting idea of the exchange of spinning massive particles, which produce these new types of shapes shown here, which we didn't look for before in Planck. I'm just previewing the fact that we have looked for them now. There's a paper coming out within a week about a comprehensive search through all these cosmological collider signals using the Planck data, and so we'll get state-of-the-art constraints on all these models. I'll let you read the paper, but we didn't find the spin 2 particle. We only got about significance about 1 sigma for that particular signal, but it hadn't been looked for before. Okay, that's for this massive exchange. This is obviously a popular area because yesterday a paper came out from Princeton group with Cabas et al., and they were looking for these cosmological collider signals. They used some of the Planck data that they had that were similar to an equilateral shape, and then they started using large-scale structure data to look for this signal as well. But that's only with SDSS, CMAS data, and so they got relatively weak constraints to those that one can find with Planck. Of course, that's going to change over time as large-scale structure surveys get better and better. So let me switch to this topic. Probably, I meant to wind up pretty quickly, but anyway, I will skip through a few slides here and talk about why large-scale structure is very interesting from a non-Gaussian point of view. And so, you know, we've got this new data. We're looking forward to what Desi says about non-Gaussianity very shortly. The idea is that these new surveys will get us down to FNLs of plus or minus 1, or even lower in the future. Remember, Planck is at the level of plus or minus 5, so this is a very significant increase with lots of discovery potential. But of course, it's more complicated because you have many more systematic effects. You have the effect of gravitational nonlinearity, which is coming in at higher order. You have redshift space distortions and bias effects and so forth, baryonic feedback. So, but already there's evidence that the large-scale structure is going to have a very big impact on parameter estimation if we use non-Gaussian information. Okay, so this analysis using the EFT of large-scale structure by these two groups, D'Amico et al., they use the one-loop bispectrum. That's the sort of next order in the bispectrum from the classical gravitational tree-level bispectrum that you predict, and they got very much stronger constraints than the other group doing this analysis, okay? Certainly on non-Gaussianity, but also on breaking other parameter degeneracies. Okay, and so the forecast for the next decade may be that we even get down to delta FNL of 0.25, and certainly improve orthogonal and equilateral constraints by factors of 5 or 6. Okay, so this is why we're developing the same methodology, applying the same methods, cranking the handle again. So I won't bore you with it, but we filter the large-scale structure. You know, we put it on a grid, filter it with the eigenfunctions, integrate them across, and that gives us our coefficients for that particular eigenfunction in the bispectrum. And so this is work we've been doing over a number of years, though we've only recently been actually applying. We've applied it to n-body simulations, looked at the effectiveness of various perturbative approximations, but we've only just recently begun applying it to, say, CMAS galaxies. What's good about these modal methods is that you can create arbitrary non-Gaussian initial conditions with it. You just create a Gaussian random field, and then using whatever theoretical bispectrum you want to have, you filter, you know, with your eigenfunctions, and then you add the theoretical coefficients to the data. This is the non-Gaussian part that you just add, and you can create non-Gaussian initial conditions, which we've done in the past. And here's an example of the theoretical bispectrum that you're trying to put into the data, here's here is the one extracted from this. I forget how many simulations, but maybe it's an average of about 1,000 simulations in the indistinguishable. Okay, so there are many benefits from using these separable modal methods. We are able to converge. We're able to do up to 5,000 modes, extract all the information there is in the data, and look for high resolution bispectra, feature models, and so forth without difficulty. Okay, so but I'll press on. Okay, this is work with David Baker, and we're currently writing a methodology paper about the effectiveness of this and how efficient it is. I just wanted to comment also that the effective field theory of large-scale structure is a very important aid in making this connection between fundamental theory and large-scale structure surveys, because we really want a quantitative basis for eliminating the late-time nonlinear clustering, and effective field theory of large-scale structure allows us to extrapolate it into the quasi-nonlinear regime much more effectively. So here is, for example, the first approximation. This is the tree-level bispectrum that you predict from the next order calculations in perturbative theory. Here's what you get from an n-body code. You can see there's a lot of power missing as you get to higher and higher modes. But the effective field theory of large-scale structure at the one-loop level, if you go and do the next order calculation, you get a very good representation of what n-body codes give you that other methods don't appear to manage very well. Okay, so effective field theory of large-scale structure has got these additional degrees of freedom. You've got counter terms and so forth, but it extrapolates much better to match n-body data than other methods. I just want to comment also that the bispectrum is interesting sort of morphologically. You can see how the bispectrum changes as large-scale structure evolves. When you sort of first, you always collapse in one dimension first with gravitational clustering, and so you see a sort of pancake form. As you start filaments, you start getting a sort of squeezed signal, and then as everything clusters into point-like particles, then you get the constant bispectrum, okay, in highly nonlinear regimes. So it's, the contrary to sort of expectations for higher order correlators, they're actually well behaved in the highly nonlinear regime, and they have a particular relationship with the third and the fourth order correlation with each other, and so they're probably very useful diagnostic tools for distinguishing between different types of simulations, hydro simulations, and so forth. And we find we can get a very good match with a phenomenological model where we have three types of non-Gaussianity inspired by the one halo, two halo, and three halo models. Okay, so this might make a fast prescription for making mock catalogs with the correct bispectrum. Okay, so just the final remarks about the tomographic large-scale structure estimator that we're also working on. And that is interesting. This is Alex Maranthes' work. And that's interesting because we want to cross-correlate large-scale structure with other things which are sometimes two-dimensional. So the CMB lensing in particular. And so actually I should have got this reference here, but Farron et al. Recently discovered this strong correlation between CMB lensing and the galaxy distribution. That's just one example. Okay, and if you do tomographic analysis where you put your galaxies on redshift shells, then you suppress radial modes. You can remove redshift space distortion effects and other evolutionary effects. So here's our projected bispectrum again. Okay, and once again, you always benefit from using separable techniques so that all your integrals break down. Here, it's really quite complicated because this looks to be the same as the CMB projection, But in fact, we had all these transfer functions before, and here we're just projecting from 3D space into 2D space. And the transfer functions were very useful, actually, because they had lots of damping on them, and so they provided natural envelopes that cut off some of the high-frequency signal. And so this doesn't happen when you do the direct projection, and so we've had to use FFT log methods, and so Alex has pioneered how to do this successfully. And anyway, so here are a couple of these, this is projecting the theoretical bispectrum into the two-dimensional space. So here's the tree-level bispectrum. The weighting is different when you project your bispectrum, so the signal drops off as you get to large L. And here's the local type shape with a sort of squeezed limit. And so here's some results from the CMAS galaxies for the projected bispectrum. This is just very preliminary, so that we've got those data. We have to in-paint around the edges, just like with Planck, to remove nasty edge effects which affect eigenfunction expansions. And we've got lots of mock catalogs provided by the collaboration to look at. And so here it is. This is the reconstructed bispectrum of the CMAS galaxies. And you can see it's largely a signal on the front face. And there's a bit of a squeezed part to it. And if we look at the mock catalogs that were provided with this data set, we see a very similar averaged. Individually, the bispectra look very similar, but this is the average. And we get a very consistent sort of result here. And these correlate well with each other. And here is just the tree-level gravitational bispectrum. And you can see it does not project as far. So we're seeing the evidence of sort of nonlinear clustering. We would do better with a one-loop bispectrum for modeling this particular signal. Okay, so that's just some early results for that. I just want to finish by saying non-Gaussianity is now a very interesting cosmological observable. It gives us the first unambiguous look at nonlinear interactions, nonlinearity from gravitational collapse. And there are excellent prospects for this information to improve dramatically with future CMB experiments and large-scale structure surveys. So that's the end of my little overview. Thanks very much.
All right. Now, the discussion session. Any questions? Yeah.
So in your interpretation, you relied on models of inflation, and there was almost an infinite number of them, as far as I'm concerned.
Yeah.
More than the uncertainties in the data. So my question is, do you envision a future in which inflation will be tested, or you think we will just reverse engineer it? In other words, is there something that will basically violate your belief system about inflation that you can think about, that if it's detected in the sky would tell you inflation didn't happen? Or anything that happens in the sky will be explained by some model?
Right. I tend to like the idea that one looks at well-motivated models of inflation, which are somehow coming out of fundamental theory, rather than engineering arbitrarily baroque potentials in order to match the data. So the simplest models of inflation, with monomial potentials, are obviously under a lot of pressure at the moment. They're getting ruled out by bicep results. And so I think there is a good prospect that this data will provide useful information that will actually constrain the range of possibilities that are available. But it's true that there are many more models of inflation than there are researchers working on inflation. With André Linde, the worst culprit for inventing many more models. But each of these types of models, like axion inflation, that's well motivated for several reasons. You know, the dark matter problem because of various fundamental issues in particle physics. And so if one found a resonance type signature that had some logarithmic dependence on the periodicity, then you would take that model much more seriously. Okay, so it does presume that there will be a hint that will guide us somewhere. But the other issue is if we continue to drive this down like this, eventually we'll see something. You know, there has to be something. Even slow roll inflation eventually, you know, if we keep going down, we'll see the...
At which point will you say inflation is not valid because it's too small?
Well, we've got a while to go, so...
well, I'm just asking, like, is 0.1 too low?
0.01 would be trouble.
For FNL?
Yes, that would be
Okay,
very,
so
very...
if you get to 0.01, you say inflation is in trouble.
Well, you can. I'll pass this question on to Xing
How
Yang.
low can FNL be?
Yeah. So in principle, it can be even lower. So you still rule out the simplest model of thing.
It's not possible.
Yeah. So it's true. I mean, there are many observables, right? So most of observables tells you what models of inflation you are selecting, but there are a few of them which can tell you it's most likely not from inflation. For example, some signals of massive field we worked on previously. And also, some signals can significantly rule out any non-inflation models. For example, the tensor mode John is searching for. So there are such observables. So you need to really carefully categorize among so many observables which are the ones tell you models and which one tell you is inflation or non-inflation. Yeah, but there are some, very few. Yeah, this local non-Gaussian is not one of them, unfortunately. Yeah.
When you actually go and get this primordial bispectrum thing and start making real models, it's actually very difficult to fit the data. So you know, I think when we get it's quite possible we'll find a signature that will guide us about, you know, give us insight about the early universe.
Yeah.
I mean, it's such a dramatic extrapolation into the early universe that we can go to such high energies with this very credible theory of where the structure in the universe came from quantum fluctuations. And we're just looking for that's the linear prediction. We're just looking for the nonlinear correction to that from interactions. And I think that's a very reasonable way forward. It's very perturbative. And inflation's a great theory because it's just a sort of extrapolation into the early universe where we can use quantum field theory in curved space-time. We don't need to use quantum gravity. We've got, you know, it's a perturbative prediction. So the trouble with the alternatives to inflation is they generally sort of bounce the universe through some quantum gravity regime about which we know nothing. We know nothing about fundamental theory, really, and that's what this might teach us if we find that extra little signature around the linear predictions. We'll learn more.
Yeah, I think, Paul's right. So inflation also has an advantage. It's calculable. That's why, there's a reason so many people like it. Non-inflation model even have a problem for theorists to calculate it. Yeah.
Right, but that's like saying the keys should be next to the lamp.
Exactly. The nature does not care about calculability. So we should keep working on that, right? Any questions? Yeah.
A very elementary technical question. So you talked about these different eigenfunctions that you can use, separable or truly orthogonal and all that stuff. That's a choice you make, but at the end of the day, do you calculate the exact bispectrum, or does each such choice lead to some approximation in the final product?
Yes. So Yeah, each eigenfunction expansion only has a, it's approximating the final shape. But certainly we make approximations that are well below, the threshold of observational differences. Okay. So, but it's true, yeah, you can choose Fourier series, for example, or Legendre polynomials, and they give you a slightly different pi spectrum. But we're always checking the convergence of it, and there's this, I skipped over this total correlator, but it's essentially the sort of observational error you would get by having an imperfect eigenfunction expansion, and we always keep that well below the observational error, but far below, actually.
I mean, the reason
it's
I'm
not a
asking
problem.
is, in my mind, a separable assumption looks like a very severe simplification, but you still think that it's manageable.
Yes, so people presented all these bispectra which appear not to be separable, though ultimately, when you see how they're calculated, they are separable in some fundamental sense. But we were able to approximate them at arbitrary accuracy with separable eigenfunctions. And that made the whole calculation of the transfer functions and so forth, the projection, completely tractable. Okay, so that's the important thing. Yeah, we haven't found anything that we can't approximate with separable. I'm sure you could come up with some fractal or something. But,
We have a series of them. It's like a Fourier decomposition. You can always do if you.
You can always do it. That's the part that's bothering me.
Yeah.
I
Yeah.
thought you'd be throwing out some things.
It's much more efficient than not doing
Of
the
course,
separable
that I
one. Yeah,
understand.
yeah.
That I understand, yeah.
yeah, but if you compare what we do to what the others do with Planck data, for example, they take a template which breaks into 3 or 4 separable parts, and then they project that. But that doesn't, that's not as accurate. It doesn't get the spectral index as accurately and so forth. And so, yeah. And when it comes to like feature models, you're missing whole regimes of new physics, potentially.
Okay, so predictably, I'll ask about discovery potential for improved CMB data sets.
Yeah.
So we're involved in CMB stage 4 here, and your
Yes.
bullet point up there talks about the discovery potential for oscillatory other models with
Yes.
CMB stage 4. So the beautiful Planck all-sky polarization maps have their highest signal noise at L of a few hundred. They're closest to the cosmic
Yeah.
variance limit there. And at low L and at high L, the signal to noise is worse. And so
Yeah,
there's more room
yeah.
for improvement with respect to cosmic variance limit.
That's right.
So my question is, how much of the discovery potential comes from high L? Does all of it come from high L, or is there also work being done by improving the signal to noise on the lower L nodes below L of 200 or so?
Well, generally the bispectrum weights very nicely with going up in higher L. So I think most of it's coming from higher L, actually, the higher resolution. The fact that there are systematic and bad effects down here, that might be important for models which have much more support, say in the very squeezed limit or so. So those ones. But generally speaking, the larger, the higher resolution you can get to, the more weight you get in your analysis, and that drives down your error bar.
So most of the work at the limits of our resolution and doing better than CMB stage 4
Yeah,
require vastly more signal to noise and large apertures.
Yes.
That's what I'm hearing.
Right, yes. So that's why ESO is more interesting to us than BICEP, for example, yes. So we're in ESO, sorry about that. But but we're looking, ESO is going to, have an incremental effect, but CMB stage 4 will be significantly better. But driving up here is the best way to drive down the signal, to drive down the error bars. Yeah.
Thanks.
Okay. Yeah.
Oh, yeah, just a question about this dBi bound. So you got CS is bigger than 0.075, so this is still pretty small. So, I mean, if CS is a little bigger than that, say, I don't know, 0.2 or something, it's still, I guess, a very nonlinear theory. It's still the higher order corrections are very important. So at what point can we know that the inflationary Lagrangian, if it's single field, is just second order in derivatives, just d phi squared plus small? Are we going to know that in the next 10 years or so?
Yes, sorry, I don't have a projection on the top of my head about this sound speed and its scaling with the improvements on the equilateral shape. But remember that we're talking about 5 times improvement, you know, with future large-scale structure surveys. So that limit will very significantly fall. Okay, yeah, and so yeah, it'll rule out much smaller velocities, and so deviations. But I don't have this.
You mean
You know,
rule out
I
bigger
could
velocities?
guess it'll be 5 times better, but I'm not going to. But yes, but that limit will certainly be driven down by future surveys. Yeah, and therefore, indeed, you will put models like DBI inflation. You know, they will become sort of homeopathy or something. You know, they don't actually do anything for you. Yeah, like a lot of modified gravity has become, for example. Yeah.
Well, yeah, I mean, if you get, I think you want to go the other way, higher velocities. If CS is bigger than like 0.9 or something, it's more or less irrelevant to call it DBI at that point.
Yes, that's right. That's right. Yeah. Sorry. Yeah, I should be saying higher velocities.
All right. Any more questions? So if not, let's thank Paul for the very interesting talk. So Paul, we also have a short launching talk.
Yeah, in 25 minutes.
I'll be back.
We're going to make it.
Okay.